Hello again, folks, in 113. Today we're going to be covering section 5.3. Let's see. Today is Tuesday, October 19th. So we're going to be covering section 5.3, which is two parts, I believe, in my lab. Anyhow, the packet that I have for you today consists of this older diagram. This is from, I want to say, section 10.1. So from the very beginning of the semester. All right, the information is still valuable because we're going to be dealing with primarily fractions, but also decimals. What is new is these are different methods as an overview for simplifying fractions. This is fairly comprehensive. I didn't write all of the rules of divisibility, but you have those. So that's just one method of simplifying fractions, and I'll sort of walk you through this. All right. Here's a new diagram. I just made this like yesterday or the day before. The process of converting from a mixed number to an improper fraction, or vice versa. And then since there's some similarity, I put this on the same page. If you were converting from a fraction to a decimal, which again is still on this other diagram, but just to illustrate, we want to go through that there. And then this is again an older diagram that you have, but it's useful because it has the place value chart. And then there's this, another worksheet. This is for converting from a decimal to a fraction, that is to go the other way. All right, what you do when you're dealing with a terminating decimal is the basic idea of grabbing all of the digits to the right of the decimal point and then acknowledging the rightmost place value. That would be the denominator. Versus what you do when you have a repeating decimal. This is something that really requires that you have some mastery over these three things. First of all, be able to identify place values. Secondly, know the effects of multiplying by 10 on a decimal point versus times 100 or times 1,000. And then a little inkling of algebra. Basically, you end up writing a one-step algebraic equation, right, and then solving it via opposite operations. Again, this is more or less a worksheet. I'm going to walk you through this when the time comes. Then there's the operations, what you do with fractions, multiplying them, dividing them, adding or subtracting. There is the situation when you have different denominators, what to do. All right, there's more or less sort of a traditional way of writing them, sort of stacked, versus a shortcut. And I'll show you that. The shortcut is very useful, but I would reserve this for when you have smaller single-digit numbers versus something that is like a double-digit number as a denominator. Because it can get a little, it gets less and less convenient, right? The less and less familiar the numbers are. All right. So if you're following along, do print that. Now, as to give you an overview, it wasn't worthy of a diagram, I felt, right, that I would give you as a handout. So I just sort of drew it here. What we're going to be doing today, like I said, I believe in my lab, 5.3 is broken up into two parts, if memory serves me. Anyhow, the first part will be basically simplifying fractions, converting fractions, which is from essentially a mixed number to an improper fraction and vice versa, right? And then converting from a fraction to a decimal, right, and vice versa. The second part, as you can see, is basically adding fractions, subtracting, multiplying, and dividing. But they have intricate rules that you have to be aware of course. All right. And then a multi-operational problem that would entail using the order of operations. Okay. So that is just what the plan is for today. All right. It's good to, when you're teaching little kids, especially once they've gotten to the point that they can read fairly well, say 3rd or 4th grade, do that. Let them in on the joke. So like, what's going on today? Draw them a little picture. They go, this is what we're going to accomplish. And that will help steer people on track, hopefully, right? All right, now let me adjust the lights. And we'll get going here. going to take a sip of water. Oh, this is orange juice. And we'll see how badly this is out of whack. Not too bad. I just got to aim it. We're going to have to close the blinds. And the door. Make it extra dark in here as in a vampire. There you go. That's it. Still not quite right, but there's always my world map here. That'll work. Okay, groupie. Glasses. Alright, let us start with just again a little review of an older diagram you have. Put that here. When we were in chapter 1 and part of chapter 6 and then part of chapter 10, I introduced this diagram, which I have tried to improve over the semesters. Which is to remember that, well, there's 3 different ways that you could write the same quantity. That blue is very sticky today. Alright. So this is old information, but if you were converting from a decimal to a percentage, it really just entails moving the decimal point. Right? Now, depending upon which direction you're going, from here to here, starting point is a dot, the end point is an arrow, you would be multiplying by 100. And similarly, if you were starting from a fraction and converting to a percentage, it would be the same idea, just maybe stylistically looking different. So you're nonetheless starting at a fraction and going to a percent, you're multiplying by 100. If you're going back the other way, right, either to a fraction or a decimal if you prefer, then it is the opposite operation. You're dividing by 100. When you're trying to convert between fractions and decimals, which is what we're going to be doing a lot today, to start as a fraction and want to convert to a decimal essentially is to divide the numerator by the denominator, so the top thing by the bottom thing. All right. If you're going the other way, if you're starting with a decimal and you're trying to convert to a fraction, the best thing to remember is that the place value, that is the far right place value, is your denominator. And that you're going to keep all of the numbers that are involved here. You're just going to erase the decimal point. Right? You can pretty much get away with just knowing that. Right? We'll get into some more nuance of it momentarily. Now, the newer diagram I have here is this one, which is an overview of different methods for simplifying fractions. I hope that that is not too much of a glare. I'm fighting daylight at this point. Okay, now the most brute force way of simplifying a fraction, and I'm using this example of 12 over 16 several times so that you can see that you get the same result. The most brute force way is to simply employ rules of divisibility. I'm going to enlarge this a little bit. All right, and you know them, right? Most people are pretty comfortable with the rule of divisibility of 2, right? That is that if both of these are even numbers, then you should be able to simplify them by dividing by 2. Now, will that get you to the simplest form, lickety-split? Not necessarily. It may take several steps, but it is something that works, and if you feel comfortable doing that, then don't feel bad. It's making progress. So here's what you would do. All right, 12 is certainly even, 16 is certainly even. All right, that isn't necessarily the best choice, but I might feel comfortable dividing this by 2 and dividing this by 2. Just remember, sort of the golden rule of math is consistency. All right, whatever you do to the top, do also to the bottom. right? When you're simplifying. In other words, don't do different numbers at the same time. Be consistent. All right, so 12 divided by 2 would get you to 6, all right? And 16 divided by 2 would get you to 8. And then as long as you're paying attention, you would go like, well, they're still even, so in theory I could still divide them by 2. So even if you feel a little sketchy about whether you've finished or not, and usually people are when it comes to simplest form, all right, you might just be able to rely on that rule and get away with it, right? You should explore the other rules of divisibility, but for right now, 2 is sufficient. So 6 divided by 2 is 3, and 8 divided by 2 is 4, all right? And at this point, you are actually finished, all right? It is in simplest form. Again, you might feel less than secure in that, but I'll just give you the comfort of telling you, as the person in charge here, somewhat, that's finished. There's a reason for it, but I have to sort of bite my tongue and hold off on the reason why. Anyhow, as you can see, it doesn't get done in one step. It takes sometimes several steps, and it may be, quite arduous after a while, and you may end up having to shift rules in the process. Anyhow, as long as you have the stick-to-itiveness, all right, the tenacity, you will get through it. Now, bear in mind, 12 over 16 simplified is 3 over 4. All right. Why? Officially, I'll tell you in a moment. All right. Now, if you look over here at the other methods that are available to us, there's the greatest common factor method. All right. If you ever want to know for sure that you have something officially in simplified form, all right, that occurs when the GCF is 1. Now, in the case of 3 over 4, though it's superimposed upon some lettering here, the reason that 3 over 4 is indeed simplified is because if you were to analyze the factors of 3 and the factors of 4, the most that they would have in common is the number 1. And to divide by 1, as you divided by 2 twice, would not accomplish anything. It wouldn't change. What I'm getting at is that the factors of 3 are 1 and 3, and the factors of 4 are 1, 2, and 4. So what would the greatest common factor be? It would be 1, and dividing by 1 is not going to change the identity of these things. So that is the official reason that, or the official way that you can tell, sort of the litmus test, that something is finished, all right? Now, let's do this problem in the slightly more efficient, ideal way, which is to use the greatest common factor, not just something that happens to work, which is the divisibility rule of 2. All right, so it is a little more tedious, especially if you feel uncomfortable with listing factors, but this is another reason why you must memorize your multiplication tables. This is imperative that you get the kids to do that regardless of what anybody tells you, all right? If your administrator says don't make them memorize stuff, that person should be fired, quite frankly, all right? They need to memorize things when they're little, all right? It helps. Just like you learn how to spell, right? Can't rely on Grammarly all the time, can you? All right, so if you list factors of 12, do it in pairs, right? 1 and 12, all right, multiply would make 12. 2 and 6 would make 12. And then 3 and 4 make 12, all right? And as long as you, again, if you have nothing but your multiplication tables to rely on, you can get through this, all right? You could try rules of divisibility ultimately, all right, but it helps to have some frame of reference. That's what I'm getting at. Now, if you did the same thing for 16, 1 and 16 multiplied together would make 16. They're factors, right? 2 and 8 make 16. And then 4 and 4, which you only have to account for one time. All right, now as you can see, if you take the time to list all of these factors of 12 and then of 16 to compare them, you will notice that they have a lot of things in common, right? Virtually everything has the factor of 1 in common, all right? But to simplify by dividing each of these by 1 isn't going to get you anywhere, right? They even, again, we know that 2 works, right, legitimately. But what is actually the best choice? The greatest common factor. It is the best choice because it will help you get to this, guarantee that you're going to get to the simplified answer in one shot. versus several steps. And the larger these numbers are, 12 over 16 versus say 48 over 96, the more arduous it becomes. And you have a little bit of a harder time telling what is finished or not. Anyhow, that's the GCF. So if you took 12 over 16 and you divided by 4 instead of dividing by 2 twice, you will get to the answer. What is 12 divided by 4? It's 3. And what is 16 divided by 4? 4. 3/4, which we already know is the answer, right? It's more efficient, and that is ultimately why we are taught the greatest common factor, okay? There is the amped up version of this, which is to use prime factorizations, right? This is a little bit more tedious, but it is worth exploring, so let's take a look at that. You already know what the answer is because we've done it twice. Scoop this over. If you remember, to get the prime factorization of a number, you might use factor trees, or you might try that newfangled method of upside down division by prime numbers. Right? Whichever you feel more comfortable doing is fine. All right. Let's say I did 12 via factor trees. You would attempt to break down the number into just prime numbers, which means that you do need to memorize, once again, what are prime. 2, 3, 5, 7, 11, 13 is a good frame of reference. So even if you started with 2 times 6, you're making progress, don't feel bad, just stick to it. Right? 2 is prime, 6 isn't, but that will factor into 2 and 3. And this 2 times 2 times 3 is your prime factorization of 12. So I'm going to put it in sort of descending order here. And if you did 16, I'll try it the other way, the upside down division by primes method, which is to put 16 in a box like this, and you start with the lowest prime number that happens to be divisible. It's even, and 2 happens to be a prime number, so we could use that. We're going to keep dividing by 2 until it doesn't work anymore. Until we've exhausted it. 2 goes into 16 exactly 8 times. Does 2 still work? Is it still divisible? Yep. So you're going to keep using 2 until it isn't divisible anymore. All right. 8 divided by 2 would give you 4, and that again is still divisible by 2. All right, so we're going to use that. And you stop when the quotient is also prime, because we're looking for a prime factorization. This gobbledygook that you see in the end here, all primes, is the prime factorization of 16, instead of doing it as factor trees. So, 2.2.2.2. Okay. Now, if you've taken the time to go through this method of establishing prime factorizations for the purpose of simplifying fractions, then you get the satisfaction of crossing out stuff. If you have things that are in factored form, that is, they're separated by multiplication dots, essentially, or you can put them in parentheses, cross out the pairs. All right? Legally speaking, you can do that. All right? So here's a pair of 2's, and here's a second pair of 2's. All right? And anything left over, as you can see, there's just 3 on top, is the new numerator. And anything that is left over on the bottom, you could recombine. That is the denominator. 2 times 2 is 4. Right? So that's 3 different ways to get the same answer. Right. Now I did include one other thing, which is a shortcut, though. It isn't really, it's not as, I don't want to say it's incorrect, but it only works under certain circumstances, as shortcuts often do. So let's take a look at that. Okay, now I gave you 2 examples here. This shortcut will work for simplifying fractions that involve round numbers, so that is to say something that has a lot of zeros in it. You could, in a similar way to crossing out pairs of factors from the prime factorizations, you can get away with, and I really can't stress that enough, this is a shortcut, so you're more or less getting away with something. crossing out pairs of zeros. Right? So if you see an example, extreme cases, say 300 over 400, if you cross out a pair of zeros, you're getting closer to the simplified form. If you cross out a second pair of zeros, then you're pretty much done. You already know that 3 over 4 is as simplified as you can get. Just a coincidental number. Anyhow, what is the actual logic behind this that you're not really wanting to dwell upon? It's like dividing by 100 here and 100 here without really thinking about it. Right? Anyhow, that would equal 3 over 4 again. 10 over 20 is again like dividing this by 10 and this by 10 without really thinking about it. So this would be equal to a half. All right, that is a useful thing, the shortcut, but realize that it only works under certain circumstances, and there is a legitimate reason why. You're really dividing without really thinking. Just don't do that when you have something like this. You don't want to see, oh look, 16 over 26, and then go, ooh, pair of sixes, all right? Done, 1/2, right? Because that's not the correct answer. You can't do that in this case, all right? You would see that if you reduced 16 over 26 legitimately, it's not going to be a half as an answer. Those are not factors unless they're separated by dots, all right? They are the actual number. So you would have to divide by 2 in this case, looks like, and you would get 8 over 13 in that instance. Okay, which is quite a different number than 1/2. It's exceeding a half. Okay, so just be aware of that. You have these different techniques for simplifying. If you happen to have this kind of a calculator, all right, you can of course get it to do that for you. There's a button on here, which I'm reluctant to tell you, ABC, all right, which allows you to enter things in the style of a fraction. Say for example that last one, if you hit 16 or enter 16 and then press ABC, you'll see that it then enter 26. It has a sort of a funny way of indicating that this is a fraction by sort of a backwards L, if you will. That's the fraction bar. All right. If you just hit equals, it will reduce it to what it's supposed to be, 8 over 13. All right. But don't abuse this. With great power comes great responsibility, right? The old adage goes. It's true. All right. Even if we have a machine, which is great, you know, when you've gotten past the point that you have assimilated technique and material, that's fine, use that, but don't abuse it. And you don't want your kids, especially in this day and age where they have access to a calculator virtually every second of every day because they have a phone, take that away. You have to, and especially in the primary years, right? In K through, I would say at least junior high, you know, middle school, K through 6, right? You have to make sure that they know how to read, write, and perform basic arithmetic without the use of a machine, right? It's great to acquire the skill of using a calculator because it is certainly a skill and it is helpful, but don't make them circumvent the mental exercise, right? I can't stress that enough. It's very important. Right? They have to know how to do things by hand, right? They'll grasp material in the long run much better. Okay. All right, now let's get into this converting from mixed number to an improper fraction and vice versa, which is this slide. And I have to clean up my board a little bit. This is again an overview here. So this is the actual, you know, sort of technical terminology, right? When you see a mixed number, which I've abbreviated just by the word mixed, and this is improper fraction. A mixed number is something that has a whole number up in front of a fraction, right? And the fraction's parts are the numerator and the denominator, respectively. Right? It's a little bit easier when you're talking about it to go with the big number in the front and the top and the bottom of the fraction. Right? If you're converting from a mixed number to an improper fraction, this is basically the process right here. Right? Which may be a little hard to see, so let me zoom in on this. You're going to multiply the whole number, the big number, times the denominator. So big times bottom, if you will. And then add that to the top. And whatever you get from that sum, that becomes the new top, the new numerator. And you keep the same denominator, same bottom. So as an example, suppose you had, I'll draw this on top of it, and hopefully it will be visible. Suppose you had 2 3/5. If you follow this process, right, it's these two things multiplied together, which is 10, which you add to the tippy top, right? That would be 13, and then you keep the same denominator, 5, right? So 2 3/5 ends up being 2 times 5 plus 3 is 13 over 5. I'd like to try to do this when I'm doing it myself by hand as sort of a hand gesture, you know, it makes it somehow more conducive to me. All right, let's do another one. Sometimes it's better than the verbal explanation, although I would be negligent if I did not include that with this. All right. Here is 4 7/8. All right, it's 4 times 3, 32, added to 7, which is what? 39 over 8. All right. To have to verbally explain the intricacies of, well, it's going to be the whole number times the denominator added to the numerator, and then you keep that, and then you keep the same denominator, it's a little bit more cumbersome to explain to a little kid. But if you have sort of a visual aid of some sort, and you realize that it's more or less sort of this circular thought process, I think that might be helpful. Right. Now, here's, if you're going the other way, if you were to start with an improper fraction, and just for the sake of theory, what is an improper fraction? An improper fraction officially is a fraction that if the numerator is greater than or equal to the denominator. So we don't, like, that technically means that if you had 7 over 7, that would be an improper fraction. We don't usually think of it as that way, but we always say, oh, it's when there's a bigger number on the top, right? That's true, but technically speaking, it could be exactly identical to the denominator. So if you had either 7 over 7 or 8 over 7, that's a classic example of an improper fraction. All right. All right. Now, what is the process here? As stated previously, it's essentially dividing the top by the bottom. So if you had, let's just say, 8 over 5. Right. What I was taught to do, and I want to encourage this because I think it's practical, is you sort of, when you have the fraction typed onto a piece of paper, let's just simulate that, what you do to save time is you draw this division box adjacent to it, because then the denominator is already right where it's supposed to be, in the position of a divisor. Right? And then what you just have to do is to drop the numerator inside, right? And that's in the position of a dividend. So it's a little bit faster. Now I did include a decimal place here, just for future reference, really. If you're converting between an improper fraction and a mixed number, you're not going to involve the decimal, really. But where would it technically be? It would be after this digit, right? And then you would make sure that it aligns with the top quotient here. In the case of improper fractions converting to a mixed number, you're counting on there going to be a remainder, right? So at this point, what you have is this. You have 5 into 8, right? Go through the trouble of doing the subtraction and writing the quotient where it's supposed to be. How many 5s can you squeeze into 8 roughly? Just 1, right? And then you perform the intricate subtraction, right? 8 minus 5 is simply 3. Now, that's a remainder, right? You want the remainder because the remainder becomes the top, right? And whatever was the denominator to begin with, you keep that same bottom number. So if you have a 3 here, rather than put R3, as we are taught when we're maybe in first or second grade, what you're going to put is 3 over what you divided by, 5. So 1 3/5. Okay. Here's a slightly uglier one. Say you had 225 over 8. Seem to like 8s, don't I? Alright. Again, you draw the division box adjacent to it. And you drop 225 on the inside here. In the position of the dividend. Alright, now 8 goes into 22. I hope that's not too hard to see. That's a little better, right? 8 into 22, roughly, 2 times. Try to keep these aligned. This is why graph paper would be a handy thing to make a kid work with when they're learning to write. Neatness helps. Bear that in mind, all right? Not to really go off the subject here, but if a kid makes a mistake, a lot of times it's not that they don't understand the concept, they just have sloppy handwriting. So give them the scaffold, give them the graph paper that anal attentively aligns things. I know that sounds crazy, but if they give kids paper like this, right, to learn how to write their letters, then they should give them paper like this to put their numbers in. You know, it's a scaffold. Anyhow, 2 goes into 22, 8 goes into that 16 times. That's 2 times 8 is 16, and then you subtract, right? This becomes 12, that becomes 1, the difference is 6, direct down to 5, readdress the question. How many 8s can you squeeze into 65, roughly? If you know your multiplication tables, you know that it would be about 8, which is 64, right? And then the difference is 1. I'm kind of hanging off the board here, right? We're not doing decimal conversion here, we're just going to go with a mixed number. So we have a remainder here, which is 1 over 8. This is 28 and 1/8. Right. 225 eighths is 28 and 1/8 in mixed number style. Right. Okay. Now, another thing to mention, all right, why learn your multiplication tables? Because when you need the frame of reference when you're trying to perform the opposite operation, namely division, right? So a grave injustice has been committed against an entire generation of students, unfortunately, in the United States, where we said, don't memorize stuff, which is crazy, all right? All right, when you're a little kid, you're 8 years old, you're not a scientist yet, we have to train you to be analytical, but the most basic way of learning is to memorize information. So it's very practical in those years, you know, to learn to memorize spelling and multiplication, right? Again, why? Because you need a frame of reference. You have to build that up, right? Yes, you could look it up in a book, but you don't always have one, right? Yes, you can use your calculator, you can use the internet, right? But that's circumventing the mental exercise. It's not helping, right? Now, because it is related, I included on this piece of paper this similar looking process just adjacent here. you'll notice that, remember from a while back, if you were going to convert from a decimal to a fraction, or pardon me, a fraction to a decimal this way, the purple arrow, it involves dividing the top number by the bottom number. Well, we were just doing that. The only difference is that we were taking remainders into consideration to arrive at the new numerator, right? A remainder is basically used as a numerator, right? And the divisor, the bottom, is the denominator. Same bottom. Now, similar process when you're starting with a fraction and you're going to a decimal, except that now you're going to explicitly intentionally put a decimal point, right? I only included it here because I wanted to see where it would technically be, right? But now you have to, when you're doing a fraction to decimal conversion, put a decimal point, make sure that it aligns with the decimal that would be in the quotients. This is again why graph paper would be handy. And then to get yourself rolling, put some zeros in here, right? Because you're not going to stop dividing until it either terminates or it repeats. In other words, you see a pattern, right? Continue to divide until either terminates, that is your quotient, right, or it repeats, right? Repeating is when you see a pattern. Okay? Terminates is that essentially when the remainder is equal to 0. All right. If you have a pattern, like say it's 0.77777 into infinity, use bar notation. I know this is a little bit too far away, so. No, don't show me that. Use bar notation, right? To indicate a pattern. So you probably know already, but just to reinforce this concept. If you had a decimal number like 0.777 repeating, it is either illustrated as following that pattern by ellipses, or the abbreviation 0.7 with a bar just above one digit that repeats. If you had more than one digit repeating, like 181818, the way that you can abbreviate that essentially is to extend the bar over both pieces. Okay? Anyhow, the process is still the same. Fraction to decimal, divide the top by the bottom. Okay? So here's an example. If you had a terminating decimal, say you had, a terminating fraction, it is a terminating decimal, like 3/10, all right? If it was written like this on a piece of paper, right, then indeed what would you do? You'd build up your box here like this, and then you have the 10 in the position of divisor automatically, and then you sort of plop the numerator in here, right? Then you put a 0, decimal point, and throw in some zeros. You may not end up needing a lot of them. You may just end up using one, but use 3. All right, it's a good sort of rule of thumb. All right, now you continue. All right, 10 does not fit into 3, so you would put a 0 here to fill the void. And again, graph paper would be great to keep everything aligned, because you know when you add and subtract, you end up having to subtract in these cases, right? Long division. You want to make sure that things line up correctly, right? 10 will fit into 30 exactly 3 times, of course, which is 30, and the difference is 0, right? The remainder is 0, so this is a terminating decimal, right? Therefore, three-tenths is 0.3, of course, right? If you know your place values, which is again the other reason that I included this old diagram, which I swiped from your book because it's nice, all right? The name indicates what the fraction denominator would be. Right? Here's a slightly uglier problem. Suppose you had 1/3, right, and you were going to convert this fraction to a decimal. Again, draw the division box adjacent. Right. That leaves you 3 in the position of the divisor where it's supposed to be, and you put the 1 in here. And then, just to get it rolling again, put in some zeros. Make sure that the decimal point lines up. And again, if this was on graph paper, it would be ideal. I'll go through the process. All right. 3, how many can you fit into 1? 0. So you put in a placeholder. But 3 goes into 10 3 times approximately, which is 9. And the difference would end up being 1, which leaves you with the thing you started with. And if you're clever, you're unfamiliar, you'll go like, oh, all right, it's a repeater. But even if you didn't, then you would bring down the next 0, and you'd go, all right, let me do this again. 3 goes into 10, how many times? Well, it's 3, isn't it? And then you do 9 again, subtract, you get 1 again. You go, oh, okay. And eventually you catch on, right? You go, wait a minute, I'm seeing the same figure again and again. Right? And you end up subtracting 9 and getting 1 again. And this will repeat infinitely, right? So, you could say 0.3 with ellipses, or you could say 0.3 with a bar over it to abbreviate. All right, 1/3 is 0.3 repeating. Okay, 3/10. It's not 3/10 unless it terminates. It's just 1/3. All right, technically it would be 3/9. Okay, all right. Now, let me show you an interesting one. Because it's famous. We'll take a slightly more exaggerated example here, but we'll do the same thing. If you used the famous improper fraction, and there is indeed a famous improper fraction, (22/7), you can convert this to a decimal, right? Same process as previously. So I'll put it here. 22/7, and I'll draw a box like this. And although it is a little bit over the top, I feel compelled to use my t-square to simulate graph paper. So humor me for just a moment. Band-Aids come off. Let's do this. All right. Brute force, because it will get the point across. Never feel bad about doing something brute force, especially the first time, because the experience is how you remember to do things. Right. That encourages actual learning. All right. So if you have 22/7 and you're going to convert to a decimal, by now we've established that, well, you just have to put this in here. All right. 22. All right. I'm going to put the decimal point right here, all right, and then throw in some zeros to get going. We may end up needing more than this. Likely we will, but let's go through the process. 7 goes into 22 how many times? 3, which is 21. And if you subtract these, the difference is simply 1, right? It didn't terminate because it isn't a 0, so then you do need to bring this down. and then you go through the process again. How many 7s can you fit into 10? 1, which is 7 itself, and then you subtract. And at this point you go, oh, it's 3. Okay. Again, didn't terminate, so you're going to keep going until you see a pattern of some sort, or if it terminates. So you bring down another 0, you go, oh, 30. All right. 7 goes into 30. How many times? About 4, which is 28. And you subtract them and you get 2. You go, man, this is annoying, this one. And you go, all right, well, here's another 0. And you know, 7 goes into 20 roughly twice, which is 14. And the difference is 6. Right? Now I'm sort of running out of paper, right? I'll make do. You bring down a 0 because it didn't terminate, and you have 60. And you go, all right, 7 goes into 60 how many times? Roughly 8 times, which is 56. 60 minus 56 is a difference of 4, right? And then you would need another 0. Right? And yes, I'm going to bother to do this because it's important. So humor me just a moment longer. And I think that should be enough. What you would end up doing is throwing in another 0 here, carrying it down to 40, and you go, all right, 7 goes into 40 roughly how many times? Right, 5 times, right, which would be a different, that would be 35 that you then subtract. Right? And the difference of 40 and 35 is 5, and you go, this never ends, right? So then you throw in another 0, and you drag that down, and now you have 50. You know, 7 goes into 50 how many times? 7, which is 49, and then you subtract those, and what do you end up getting? Right? You end up getting 1, which is a digit that you had previously, right? So without going through the trouble after this point of throwing in another 0 and then going, oh, it's 10 again, it is predictable what is going to unfurl here if you were to continue, right? You're going to essentially get 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, 1, and so forth. This is an example, a famous improper fraction, an example of an incredibly long repeating decimal, because it's not just 1 digit or 2 that repeats, it's 1, 2, 3, 4, 5, 6 digits before the pattern continues, right? So what you would end up having to do to abbreviate the answer here is to write this. You would have to say that this is equal to 3.142857 with a bar above all of the digits from here to here, from 1 over to the 7. All right. Now, why is this a famous repeating decimal, 142857? Because it's an approximate for pi. And pi is an example of an irrational number that everybody should learn before they leave grammar school. Now, normally, what do they tell you? Right? When you're a little kid and you first are taught about pi, maybe 3rd or 4th grade in the United States, we have the symbol for pi, the Greek letter P, to make it fancier. Probably not doing any justice, but we have a Greek letter to represent the quantity, which we're usually just taught to memorize up to the 100th place, so 3.14. If you have a graphing a scientific calculator that comes with a pi button, as we do in our case, you would see that although it is remarkably similar, your calculator would specify, here's the pi button here, and there's pi on the screen, and here's the decimal equivalent, that it should be at least up to the edge of the screen here. There's 10 decimal places. 3.14159. Two, 6, and at that point there's things that follow it. Right? It's not really a pattern in this case, so I really shouldn't technically use those ellipses or anything. But notice what 22 over 7 is. Right? 22 over 7 is 3.1428571. Right? They are similar enough up to the hundredths place, right? Once you get to the thousandths place, they're no longer the same figure. So perhaps you, like me, you've been misled. When I was a little kid, I was told, well, 22 over 7 is equal to pi, right? But that's not really true. They're not equal, as you can see, right? This is an example of an famously irrational number, right? Which means it can't be a fraction. All right? And this evidently is a fraction. All right? So why do we use 22 over 7 sometimes when we're involving it in geometry? Because it is an approximate. 22 over 7 is an approximate for pi, right? Just understand that does not mean equal, it just means remarkably close. So it's practical. If you had a problem like, area or perimeter, area or circumference of a circle, which would entail using pi at some point, if you're not using simply the decimals 3.14 or even 3.14159, right? A lot of times you're encouraged to use 22 over 7. Why? Because it just happens to work well with other fractions and it's really close to pi. Okay? So do be aware of that. I'm not that boring, am I? Okay. Alright, I'm going to get a sip of water and I'll be right back. All right. Now, let me discuss this other thing. Okay. There's a diagram. Let me get rid of this now. Yeah. For when we're converting the other way. Right? We have been doing basically this to this point, fraction to decimal. Let's say we're going the other way. Depending upon what you have, you're given, right? You might do it one way versus another. So that's what this sheet is all about. Right? In general, if you want to convert from a decimal to a fraction, you're given a terminating decimal, that is, it's not infinitely stretching, this is basically the process. You take all of the digits that are to the right of the decimal point, and you make that the numerator. I'll zoom in on that. And whatever the far right decimal place value is, that becomes your denominator. So as an example, if you had 0.6, right? Think about that for a moment, the way that we say it, right, in ordinary conversation. If you were in a chemistry class and you were measuring out, milliliters of fluid, no one would have a problem if you said to them, oh, it's 0.6. But if you wanted to be a real twit, right, and you were saying it in the more formal alternative that we have in English, which is to specify its place value, 6/10ths, THS, right, tenths, all right, then we would follow this. It would tell us basically how this looks in the style of a fraction. Instead of saying 0.6, you refer to its place value. So essentially, if this is what you have, 0.6, take all of the digits that are to the right of the decimal point, which is just simply a 6 in this case, all right, and then consider what the far right place value is. This is sitting in the 10th place, so therefore 10 is the denominator, right? And what you can do is then just whittle it down, simplify it, right? If this ends up being 6/10, try to put it in simplest form. Right? The GCF is actually 2, so that's the best course of action. You end up getting 3/5. 3/5 is the simplest form of 6/10. Okay. If you had something that was much uglier, say something like 0.475, all right, as long as you remember you're going to take all of the digits to the right of the decimal point, all right, that means 475 would be the numerator here, and then consider what the far right place value ought to be. Now, again, you need to remember, if this is the 10th place and this is the 100th place, then this is the 1000th place, THS. All right, so that is a denominator of 1,000. 475 thousandths is kind of an awkward way of talking, but that is the formal way of saying it in English, so to speak, correctly. Anyhow, no one's going to get mad at you if you say 0.475. In fact, they probably would like that better. If you were going to simplify this, ideally you should use the GCF, but if it's less familiar, all right, you could try rules of divisibility, which is to divide each of these by 5 since they end in a 5 or a 0. Or if you're more daring, maybe try like 25, because you might recognize some of these numbers from dealing with money, right, like quarters of a dollar. So I'm going to go that route just because it happens to occur to me. It isn't necessarily the GCF though. I really should take the time to get the prime factorization in a case like this. 25 goes into 47 roughly one time. And the difference would be what? Looks like 22. So I'm going to carry this as 225. 25 goes into $2.25 9 times, which would be 19. And then 25 goes into 100 4 times exactly. And it goes into 0 times. So that should be 19 over 40 if I'm not mistaken. Now, again, you can do to verify is, we'll try this with your calculators. This is a prime opportunity. Clear, I'm doing logarithms. 475 ABC over, let's see, that's a 1 down there. 0, nope. Don't do it like that. 0, 0, 0. There you go. If my calculations are correct, 475 thousandths should be 19 over 40. Good. All right. Predicted correctly. Okay. All right. Anyhow, that's the process. Now you might say, well, what if you had something that looked more akin to a mixed number? No sweat. It's the same thing, really. You could always, if you feel like it, attach the whole number to your fraction after the fact. But let's say hypothetically that you had something like this. 3.375. All right. That would look like this then, right? 3.375. Right? If you're just sticking with the program here, take all of the digits to the right, that's up to here. And you have 375. Again, this is sitting in the far right is the thousandths place. So therefore, this is a denominator of 1,000. and then you could whittle this down. Right? What would that make this? 3 and 375 thousandths. If memory serves me, that's the equivalent of 3/8. Right? But let me just check. Right? 375 over 1,000. Again, the GCF would be ideal, but I'm just going to try 25 because I'm comfortable with that. All right, and we'll go through it. 25 goes into 37 roughly one time, and the difference is 12 in this case. Right? So I'm going to squeak a little 1, 2 in here and read that as 125. 25 goes into $1.25 5 times, which is 15. Right? And this is still 40. And this is still divisible by 5 and 0, so I'll continue with that. And slowly but surely whittle it down. 15 goes, divided by 5 is 3, 40 divided by 5 is 8, 3/8, right? So 3.375, or you could say very officially 3 and 375 thousandths, right, is the equivalent of 3 and 3/8. That's a little hard to see, right? Okay. If you want, in reality, what you could do, if you wanted to write something in the style of an improper fraction, you could just take the whole kit and caboodle, right? And then just get rid of this decimal point. Then you have 3,375 over 1,000, right? Notice it's improper because you have a larger numerator than you do a denominator, right? And at this point, you could whittle that down to whatever the equivalent, simplest form of an improper fraction would be. Okay. If there happens to be a minus in here as well, all right, just tack it on to the outcome. All right. Now, what about those instances when you have something that is a repeater? That's over here. Let me back this off just a wee bit. All right, well, this is a little bit more involved. Okay, I tried to summarize this, and there's some prerequisite knowledge and skill that a person really must master before you start dealing with converting a repeating decimal to a fraction. All right. Some of it's pretty easy, and you're already well familiar, but let's walk you through it here. All right. No, I don't want that. Firstly, all right, know your place values. All right. If you have a digit, and I just used 1, so I'm not too creative. If you have a 1 sitting in this position, that's 2 spaces up to the left of this decimal point, that is the tens place, of course. If you have a digit that is sitting in the 1 space to the left, it would be the ones place. All right. Then you have a digit to the right is tenths place. All right, there's no 1th place, right? So it's tenths, hundredths, and thousandths, right? Know those. If you pretty much, you should know beyond them, of course, but when you're doing your conversions between fractions and decimals, it's usually the extent of what you'll see. All right. Know those because you need them as a denominator reference. All right. Then there are these mental math skills which are very handy. All right. Remember the effect, all right, from when you're converting from decimals and percentages. All right. That if you multiply a decimal times 10, the effect without going through the intricate multiplication work is that it moves your decimal point once to the right. Right. So, for example, if you had 3.0 times 10, right, the effect is simply that this will scoot over 1 space, and then you end up with 30. Right. If you were to multiply by 100, the next highest power of 10, that moves twice to the right, all right? If you multiply by 1,000, it moves your decimal point thrice, technically, to the right. I put an arrow rather than spell out the word right, just because it's more intuitive, I think. But that's the direction, right. So times 10 once to the right, times 100 twice to the right, once, twice, thrice. Times 1,000 is 3 times. Okay. Next is algebra. Right. You have some experience certainly with algebra from earlier in the semester. Let me just tell you, it's never going to be too ugly. Right. This is the extent of it. Remember, in algebra, we can use a letter to represent a number, right? And that will be beneficial to us when we have to convert from a repeating decimal, believe it or not, to a fraction, right? Other than that, right, we're going to write a little teeny tiny equation that uses n to represent that repeating decimal. So you're going to have n equals whatever the repeating decimal is. Right? Now, as for the intricate work, that's what I put over here. Right? In essence, the trick to this is to preserve a segment, not the whole thing, of the pattern. Right? So if you have a repeating decimal of 0.6666666 forever, you need to preserve some portion of that when you're creating the fraction that equates to it. Right. The other thing is that you're going to be chopping off infinity, right? Chopping off the rest, because you can't, have infinity if you're going to try to do a problem. If you're doing it the rest of your life, then you'd never finish. All right. How do you chop off infinity? Well, in math world, the best course of action is to subtract. Right. And then lastly, you're going to solve what is essentially a one-step algebraic equation. Right. Now, what does that mean? If you're going to solve something algebraically, that means you're going to employ the opposite operation. So even if you set something up that it is something times something else, in order to solve it, right, what do you end up doing? If you have multiplication, you're going to divide. Right? This up here is ordinary arithmetic. Right? This is algebra. This is arithmetic. So what you see is what you get. If you're subtracting, you're subtracting. Right? In algebra, you do the opposite. All right, now, let me give you an example, all right, and we'll go through this. I'll put over one of these, my bootleg paint here. Yeah, that looks fine. All right. We're going to convert a repeating decimal to a fraction. So we already kind of know something like, we know that 0.3 repeating is 1/3, but let's say that we started with this. .3 repeating, right? Is an example of a repeating decimal, but what if we had to convert it to a fraction and we didn't have it memorized? There's a process to it. That is basically algebra. Right? Start with this. Rather than use the abbreviation, right, stretch it out a little bit. Use ellipses in this case. Now, if we're following my own instruction here, we're going to write n, a little teeny tiny little equation in which n is equal to this particular repeating decimal. So I'm going to write n is equal to 0.333 forever and ever and ever. Okay. Now I'm just going to scoot this out of the way for a moment to reveal the instruction. Remember, we have to preserve a segment of this repeating infinity. Not the whole thing. We're going to chop off some of it. In order to preserve a segment of it, we're going to take advantage of these mental math skills, which is to just move the decimal place over. So, if I have just a single digit number like 333, I'm going to try to accomplish doing this. Scooting over the decimal from where it was to just there to get a segment of the train of infinity. Which of these would be involved in accomplishing that? Multiplying by 100, multiplying by 10, or 1,000? Not in that order. Well, if you multiply by 10, that is the effect, all right? But that's going to change the number, all right? I might end up with this, all right? 3.33 still into infinity, but I can't call it n anymore, all right? What should I call it? Well, if this is just a technically 1n, right, then what this ought to be down here is 10 times n, right? Times n mutates this into that, right? Now the second part of this is that, okay, I've preserved that interesting portion of the figure, 333 forever and ever and ever. Now I gotta dismiss, chop off infinity, right? How do I do that? You're gonna do that via subtraction, okay? So let's do it, all right? If I write this original quantity, just park it underneath this, it would look like so. And what I have then is the beginnings of sort of a table of ordinary subtraction here, right? 10n is equal to 3.333 forever and ever and ever. But just to keep sort of record here, you know, if I subtract out 0.333, the original figure, what I should do is not just write it on this side, but write it on this side. That's 1n. And now I could do what I was hoping to do, which is to chop off infinity via subtraction, which is legally correct. What can we assume is true even without seeing the entirety of the thing? That if you have something minus itself, it's going to be 0 here. And even if it's the same over one extra space, something minus itself, because remember, we have this all lined up here, like good little math geeks. We have this on graph paper. And we end up with this, you know, a lot of cancellation effect, essentially, without having to physically do everything. Let's do the beginning. That would be maybe more appropriate. What is 3 minus 0? Well, it's just 3, right? That's good, all right? What's 3 minus itself, the next digit over? It's 0. Do you have to bother writing 0? Not if you don't want to. It's just as a convenience. All right, so I'm going to cross it out. And then the same thing, 3 minus 3, nah. 3 minus 3, nah. All right, and then it's just going to be, because we know it's a pattern, it's just going to be 3's forever and ever and ever. So you don't have to bother either writing 0 as the outcome or crossing them out. You can just make the assumption, right? You've essentially deleted infinity without really thinking about it too deeply, right? Meanwhile, what's going on over here, all right? The only thing that makes anything legal in math is the consistency that you employ. So if I wanted to just sort of arbitrarily create a number, it wasn't even the original number, right? I just created something by multiplying by 10. Fine. Then do the same thing over here on the opposite side of this equals. And if you subtract it here, make sure that you're consistently subtracting here, right? It's this balancing, Zen sort of balancing act that makes things legal in math world. All right. Now, you may be a little rusty, but just pay attention to 10n and 1n, right? Those are like terms, right? You could add or subtract like terms. What qualifies something as, or two things as being like terms? Essentially, they're the same letter, all right, and the same degree, which you don't really have to worry about. They would be degree 1 and degree 1. All right, the exponent. Just pay attention to the things in black here, namely the 10 and the 1. What is 10 minus 1? It's 9, right? What is the letter that they are united by? N. So 10n minus 1n is essentially 9n. Good, right? Now here's the last thing, all right? We still have a one-step algebraic equation here. 9n equals 3. How do I justify moving the 9 for the sake of solving for the algebraic equation? We are at this point, this is all arithmetic up here, we are at this point applying algebra, which means we're going to employ opposite operations. In order to justify moving something from where it is on the left to bring it over here where its friend is on the right. It is understood that two things pressed together like this, right, a number 9 and a letter N, are being multiplied. So if I want to justify the moving, I'm going to divide by 9 here, and I can make it legal and get away with this as long as I'm consistent. If you've divided by 9 here, divide by 9 there as well. All right. What is something divided by itself? All right, 9 divided by 9, 1. Do you have to bother writing 1? No more certainly than you would have to include a 0. So what are you left with? You're left with this. N is equal to 3/9. All right. Now, is that finished? Not really, but it is correct. N is equal to 3/9. Right? What is 3/9 in simplest form? Well, if you divide by 3, which would be the GCF, you'll get to it. 3 divided by 3 is 1 over 9. Pardon me, 1 over 3. All right, 9 divided by 3 is 3. 3 divided by 3 is 1/3. All right. Let's do another one just a little bit faster. Remember, the trick to this is you want to preserve some portion of the pattern when you're trying to convert to a fraction. But you also have to eliminate infinity. Right? And the way that you eliminate infinity is just purely by arithmetic, it's subtraction. So if you had something slightly uglier than just 1 digit repeating, say you had 0.18 repeating, right? And you wanted to convert this to a fraction, right? Now we have 2 digits, so stretch it out to begin with, all right? How does that really look? 0.18, 18, 18, 18, forever and ever and ever. We're just going to call this n for the sake of setting up a little equation. So I'm going to say, all right, fine, this is n. All right, now, how many digits repeat in this case? 2. So if I wanted to preserve that obvious pattern to it, 18, 18, 18, 18, I'm not going to move the decimal just one time. I need to move it twice, right, in this case. So I'm going to multiply by 100 in this case for this much of an effect. Right? So I would have 100n would be equal to 18.18, 18, 18 into infinity. Okay, now I have the portion of the pattern that is inclusive of both things that repeat, and now I want to delete out infinity here. So what am I going to do? All right, I'm going to subtract the original figure from the thing that I've created. All right, and it would look like this. Just remember, it's 1n if we have to worry about doing the actual intricate work here later. All right, we're going to subtract here, and as long as we're being consistent, I'm going to subtract here as well. On this end of it, these have to lock up all the places, right? 1 minus nothing is just 1. 8 minus 0 is just 8. That is where the decimal point would be. And then from there on out, it's 1 minus itself, which cancels. 8 minus itself, which cancels. 1 minus itself again, which cancels. 8 cancels, cancels. And the whole beauty of this is that you don't have to do it. All right. You just sort of have to understand what is happening here. Okay, now over here, this is 100 minus 1. What's the difference of 100 minus 1? 99. Okay. So, once you've deleted, without putting the zeros here, which would be unnecessary, we can now get rid of that decimal point entirely, and now perform the algebra. This again, this part of the show here is arithmetic. It's just subtraction. And what we're going to do at this point is algebra, which is opposite operation. operation. So if I wanted to solve for n, I'd have to get rid of 99, the result of subtracting the coefficient of 100 and technically 1. How do I justify moving 99 from where it is over to here, where its buddy is? Right. Again, if it is understood that two things pressed together are being multiplied, then the logic is that if I want to justify moving it, right, I would have to divide instead of multiply. So I would divide by 99 here and divide by 99 here. Right. The effect, strategically so, is that the 99s will cancel. You could put a 1 there if you'd like, but it would be superfluous. Right. And then what we would have is this, that n is equal to 18/99ths, right? Which is correct, it's just not in simplest form. So if you know your multiplication tables, you might recognize these figures, right? You go, well, 18 and 99, where have I seen that before? From the 9 times table. So 9 is a common factor for sure, all right? I'm gonna try 9. It may or may not be the GCF, I believe it is, all right? 18 divided by 9 would be 2, and 99 divided by 9 would be 11. 2/11ths would be the answer simplified. All right. You could verify again with your calculator. All right. If you had, let's say, 2. Firstly, here is the fraction that I have established. All right. 18 over 99. This is it in simplest form. All right. 2/11ths. All right. Now, what is that as a decimal? If you divide 2 by 11, what do you get? Nah. If you actually do the intricate work here of dividing 2 by 11, it's going backwards, you'll see it's 0.1818181818. Why do you see a 2 on the end? The calculator is simply rounding at the edge of the screen here. Okay. For the sake of performing a calculation rather than dealing with infinity. Right. Anyhow, that's the process. It's pretty neat, right? Right. Again, the trick to this is you want to preserve the portion of infinity that is the repeating pattern. It would be a slightly trickier problem. I don't think you'll have this in my lab, but maybe just for the sake of argument. Suppose you had something that doesn't repeat right away. So if you had 0.83 repeating and the bar is just above the 3, all right, stretch it out, all right, it would be 0.8333 forever and ever and ever, all right? And we're going to start, because we have a strategy here, to call that repeating decimal n. Okay, now in this case, all right, although the 8 is past the decimal point, it's not really part of the pattern, all right? So we're going to have to go a little bit more drastic than we would be to get the part of the pattern. We want to move the pattern to essentially the left of the decimal point, right? How many spaces would it take to get this decimal from here to just there? All right. It would take 2, which is the equivalent of multiplying by 100, right? So that means that 100n would be 83.33 forever and ever and ever. Okay. Now, if we were going to sort of jump the gun a little bit and go, all right, well, I know what the gist of this is. I have to subtract these two things. You're on the right track if you believe that, but be careful, because if you were going to put the original figure here as you see it, which would be 0.833 forever and ever and ever, it's not going to subtract everything. So what you have to do is create another new number, right? The one that is the original number is not good enough to do the subtraction immediately, so we have to do a little bit more prep work. So rather than do that, what we're going to do is just get up to the point where there is the portion of this that is repeating. In other words, if I wanted to go just a little bit further, not the whole 9 yards, if I just wanted to go from here to just there, where the 3's begin, right, that would be the equivalent of multiplying by 10, right? And then in this instance, I would have 10n is equal to not 0.833, but 8.333, repeating. This is a better choice than just 1n. We're going to use 10n when we do our subtraction. All right? How come? Because if you notice now, if I line up all these decimal places, the part of it that is genuinely repeating, namely just the 3's, is going to be deleted off successfully when I subtract now. All right? 8 minus nothing is just 8. Right? 3 minus 8. All right, I really should do this more appropriately. That's 13 and that's 7. All right, sorry. 13 minus 8 is 5, right? So 75. Okay, the decimal would be there. Now at this point, it's 3 minus 3, which is cancels appropriately. And because I have to be consistent here, if I've subtracted here, I'm going to subtract here. Instead of it being 100 minus 1, it's 100 minus 10, which is 90n. And so 90n is equal to 75. If I divide by 90 at this point, for the sake of solving for n, I must do the same thing here and here to balance, right? And then I have this. I have n is equal to 75 over 90, which is correct, it's just not simplified. Divide each of these by, I think 15 is actually the GCF in this case. So let's see. How many 15s can I squeeze into 75? Feeling that you could use 5 and 0, and you may do it in 2 steps. All right. Let's see. 15 into 60 would be exactly 4. This would be another one. That would be 5. 5 times 15 is 75. And then an additional 15 would be exactly 90. So this would be 6. 5/6 is 0.833333333. All right, let's prove that real quickly. All right, first of all, 75 over 90 is indeed 5/6. All right, what is 5 divided by 6? You see the pattern, 0.8333333 forever and ever and ever. All right, cool. All right, there's a system to it. All right, that's one thing you have to love about math. Right, it's kind of hard to sell our subject sometimes, right? But it isn't impossible. Right? Anybody that told you when you were a little kid that this is not for you, that's complete baloney. Right? It is for you. You just have to be told what the rules are. Right? It's very important to demystify. Now, let's move on to the actual operations. We've kind of done what I would argue is the hard part here. Okay. Now to summarize, this is what we'll be doing. We have multiplication of fractions, we have division of fractions, we have adding and subtracting fractions that happen to have the same denominator. Right? And then there is, in theory, adding and subtracting fractions that have different denominators. Right? So these are models that you see here, A, B, C, D. Right? Let me zoom in on each of these and make it a little bit easier to read. All right, this is the basic gist of it. All right, the brute force way of doing it is the top thing times the top thing produces a product. Right, using these letters, it would be A times C. Right, the bottom thing times the bottom thing produces this combo here, BD. Right, slightly more strategically would be to use the GCF to simplify first. Right, so in certain situations, you might want to simplify before you multiply. Right? How come? Because what happens when you multiply things is that it amplifies, right? They get bigger. That makes the task of having to simplify as an afterthought that much more arduous. So you want to spare the kid that, you spare yourself that too, right? If you happen to have a mixed number, what you can do is you convert the mixed number to an improper fraction, right? And then you just have something that fits the model immediately, okay? When you divide, it is going to ultimately be the same process, but there's a preliminary step, right? What happens is you end up multiplying after you've made a little correction, right? When you divide by a fraction, what you end up having to do is multiply by its reciprocal. Remember, reciprocal is just a fancy schmancy way of saying fraction flipped upside down. So I don't know who said this to me a long time ago, but I think it was while I was working in Staten Island, actually. One of the kids had mentioned it, and I'm like, oh, that's such a good mnemonic, the memory device, right? Keep, change, flip, right? So you keep the first fraction exactly as you see it. You change the operation, perhaps somewhat ironically, from division to multiplication, and then you form the reciprocal of the second. You flip the second, right? So this gets flipped. And then you end up doing, you have a multiplication problem, which means that if you can simplify first, do that. If you can't, then you just, do it brute force, top times top, bottom times bottom. Right? And then attempt to simplify after the fact. Okay? All right. Now, here's more or less the ideal situation when you're adding and subtracting. When you are adding, subtracting things that happen to already, what you might call like denominators. I use the same letter B here consistently. They just require you to pay attention to the top only, right? You're just going to add or subtract the tops depending upon what the combination of signs dictate. Right? And you just carry the denominator down. Don't make the mistake, a lot of times a little kid innocently will go, all right, I'm going to add this and this, and then you get something twice as large. Right? Don't do that. Right? You're just going to keep whatever the denominator is. Right? Again, if you happen to have a mixed number, do yourself, especially if signs are involved, right? Convert these to improper fractions. Right? Then you will just, again, pay attention to what the tops are. Right, and apply the sign combination rules for adding and subtracting, which is understood as being different from the sign combination rules for multiplying and dividing. That's the last lesson, right? Now, what would happen if you had unlike denominators? In this case, what is illustrated here is the shortcut, essentially. Right? But to give you the basic gist of this, you're going to arrive at some denominator that isn't what you started with, right? The shortcut is to simply combine these two, that is to, again, this is an addition or subtraction problem, but is a shortcut multiply this way, and you get that denominator. But then just realize that, remember, for the sake of consistency, if you want to get away with something legally in math world, you have to be consistent. So if you change the denominator, you're going to have to change the tops too, right? If you change a bottom, you must change a top also, right? Remember, the name of the game is be consistent in math world, right? That's what makes things legal, okay? So what I put down here is, although what you see here is true as a model, if you want to be more strategic, what you should use is the lowest common denominator, right? The lowest common denominator is the least common multiple of the denominators, right? In order to upgrade to equivalent fractions with a common denominator. That is to say, you want the smallest number possible because smaller numbers are easier to work with, right? And let's do some examples. And then we'll move on to a sort of a more thorough way of doing it. Yep. I didn't spell change correctly. Should have an E on the end there, ding dong. Okay. Let's do, I'll leave myself some space. Now, green I like to write in, but it doesn't really write very well. So I'm going to make this my border here. Here we will have 4 examples to illustrate these operations. All right, so suppose you had 3 over 5, and you use a multiplication dot times 7 over 8. Now again, it would be more strategic to try to simplify either directly above and below or diagonally if necessary. That's more or less dividing by a common factor, using rules of divisibility or ideally a GCF. If you analyze these, it's not really going to work. So you're kind of stuck doing brute force top times top, and 3 times 7 would be 21, and then brute force bottom times bottom, which would be 40. Then as an afterthought, check to see if you can simplify, all right? If the GCF is 1, you're done, okay? It's a little tedious, right? But if you analyze the factors that make 21, it would be 1 and 3 and 7 and 21, all right? If you analyze the factors of 40, though there'd be more of them, it would be 1 and 40 and 2 and 20, not 3, but 4 and 10, and 5 and 8. And as you can see, they all have 1 in common. They both have 1 in common, but they don't have anything else in common. So that is actually in simplest form. This is finished. Okay. Here's one that involves signs too. If you had negative 2 over 3 times negative 4 over 9. All right. They a lot of times in a textbook will write this with this encapsulated in parentheses, just to make sure it's not confused that this minus sign is the operation. This is a multiplication problem. All right. If you like, and I have a tendency to do this myself, just automatically gravitate these signs to the top. Makes dealing with it a little bit easier, meaning that this is what you have. Negative 2 over 3 times negative 4 over 9. Right? Now again, if you could simplify before you multiply, do so. Make it easier on you as an afterthought having to simplify. All right? But the brute force method seems to work. You can't simplify above and below the line here. So it is negative 2 times a negative 4, which is a positive 8. At that point, you don't have to worry about the signs anymore. And then it is a 3 times a 9, which is a 27. The GCF should be 1, so positive 8/27 would be your answer. Okay. If you had mixed numbers I mentioned earlier, say you had 1 and 7/8 times 2 1/4, right? What you really need to do, especially if there were signs involved here, right, is make these into improper fractions, and then you're conforming more to the model of A, B, C, D, you know. So remember, it's the big number times the bottom number plus the top. So 8 times, well, 1 times 8 is 8 plus 7 is 15 over 8. And the same thing, 2 times 4 plus 1. So 2 times 4 is 8 plus 1 is 9. So this is 9 over 4. And this is still a multiplication problem. Again, do check to see if you can simplify before you multiply. It's not going to happen in this case. So just do the brute force top times top and bottom times bottom, which stinks in this case, but so be it. All right. 4 times 8 would be 32. And 15 times 9 is a dreadful number, but let's see. 45, carry the 4, is 135. Yuck. All right. Now, my argument is this. All right. You could end up with an improper fraction that happens to be in simplest form, and if that's the case, great. But if they gave you mixed numbers to begin with, give them back mixed numbers, and this is an improper fraction. So what you have to do is divide the top by the bottom and try to establish a remainder. Okay, so it's a little cumbersome. If you want to whittle it down first, if it were possible, then go ahead and do that, but I don't think it actually is going to work. So we'll do it brute force. All right, 135 would go in here. All right, if that's about 30, and that's about 130, or if you want to round up 140, look at this in your head. Imagine that you're dealing with a 3 and a 12 instead. Right? 3 times 4 would be 12. So let's just estimate 32 times 4. Might get you close enough. Right? 32 times 4 is 8, and that's 128. That's probably as close as you're going to get to 135. So 128. Right? The difference of 35 and 135 and 128 is 7. And since you're out of digits at this point, it's 4 and 7/32. And it is your actual answer. Kind of a clunky number, but it's true. Okay. Okay. Let's do a division problem, and then we'll move into what you call it, the adding and subtracting. Okay. So if you had 3/8 divided by 5/7. All right. Remember, if you're starting with division, all right, this is an instance of where you must apply the mnemonic: keep, change, flip. Okay. So you're going to keep the fraction as you see it. You're going to change the operation, again, somewhat ironically, to multiplication, and then you're going to make the reciprocal of 5/7, which is 7/5. All right, so 3 over 8 times 7 over 5. All right, check to see if you can simplify first. Again, you can't, unfortunately. So you do brute force top times top, which is 7 times 3, which is 21. And 8 times 5, which is 40, all right, which is something we already had from earlier. Right. Shows how creative I am, right? All right. So it is, in fact, 21 over 40. All right. Let's do a couple more of these. Now I'm going to switch over to my other diagram. Suppose you had -2/9 divided by 3 over 13. Do not simplify before keep, change, flip. All right, the temptation might be there, and I sympathize really, but you don't want to do that because you'll just change it irreparably. Okay, so did I put a negative on that? I did not. Okay. So you see division to begin with, so you're going to change it according to keep, change, flip. Spell the change correctly with an E. Okay. Keep -2/9. All right, so this is still negative 2 over 9. Again, my instinct is, and I think it's a good habit too, just to not have to worry about where the sign goes, just automatically gravitate towards the top there. All right, you can put it on the bottom instead, it's just one or the other. All right, change this to times, multiplication, and then form the reciprocal of 3/13, which would be 13/3, right? All right. Now, remember, if you had done the simplifying up front, you might have went, I could simplify the 3 and the 9. And again, I sympathize, but don't do that before you keep change flip. All right? If it was multiplication, then yeah, I would try to do that. But in this case, that's bad news. All right? So, now you're kind of stuck with it. All right? Brute force top is negative 2 times essentially positive 13, which is negative 26 according to the multiplication division rules of combination of signs. And then the bottom is 9 times 3, which is 27. So what do you end up with? Negative 26/27. Right. You're kind of stuck with that. It's not simplifiable. All right. Last thing before I sort of shift gears here. Okay. If you have 19 over 24 minus 5 over 24. These have like denominators, so you don't really have to do anything, but simply pay attention to the top. Right? In other words, you could rewrite this as 19 over 5, the two of them sitting together over just 24. Right? Remember, you don't add or subtract the denominators as long as they're matching, you just keep it. Right? What is just 19 minus 5? 14. And then if it is feasible, or if it is possible, simplify it as an afterthought. Okay? So, they're both divisible by 2. So this is 7/8, it looks like. Oh, rather 12s. I'm sorry. Those are my mind. Okay. 7/12. All right. Now, let me go back to this other newfangled slide here. All right, because we're going to discuss the situation when you have unlike denominators. Right. Again, this isn't a model that is true, but it really is more illustrative of the shortcut that is involved rather than the really intricate work that works 100% of the time, or is advantageous 100% of the time. Right. There's two methods. Okay. When you have addition or subtraction of fractions with unlike denominators, I think probably people go for the shortcut more often than they should. All right. The traditional way of dealing with is to take the problem, if it's written more or less horizontally, and stack them vertically. Why? Because it makes upgrading to equivalent fractions a little bit easier when you're trying to convert. All right. The shortcut is essentially multiplying. Even though you're doing addition or subtraction, it's a shortcut, so you multiply diagonally this way, and across the bottom. Okay. What are the advantages here? Well, the traditional way of doing it is definitely going to be longer. It's definitely longer, but it's more to your advantage if you were to get into algebra when you have algebraic expressions as a denominator. All right. So I would never throw this out. All right. And the reason I would argue it is better in general is because it would be strategically using a lowest common denominator. So if you have different denominators to begin with and you want them to match, you want the smallest number possible, not just something that happens to work. All right. The shortcut doesn't care about whether it's the lowest or not. It just uses any common denominator. So it is, if you're dealing with small numbers, it's faster. Right? That's its advantage. Right? How does it really look? Well, the shortcut, again, is multiplying. right? Even if it's a subtraction problem, even if it's an addition problem, it's a shortcut. So if you multiply across the denominators, the bottoms, you establish a common denominator, not necessarily the lowest one, right? You just get one that works. If you multiply diagonally this way, you establish what would have to be the new numerator on this side of the operation. And then if you multiply diagonally this way, you establish the new numerator on this side of the operation. All right, remember, you can get away with murder in math world as long as you're consistent like this. If you start tinkering with the denominators, your hands are tied, you're obligated. You have to mutate the tops in a similar fashion. If you do it the more traditional way, which is to take the problem and stack it like this, when you're going through the trouble of using a common denominator, it makes comparisons a little bit more easy. All right, so I'm going to do the same problem two ways. I'm going to do it the harder way first, because it really works 100% of the time. All right, if you had 13 over 15, and you were subtracting 5/6. All right. Now what you would have to do is the number on the left side of the symbol would be the tippy top of this. All right. So you would put a 13 here and a 15 here, and the thing on the right of the operator, 5/6, would be underneath it. Now, the first thing is you want to establish a common denominator. Right? You can't legally add or subtract until the denominators match. So what you want strategically is the lowest common denominator, right? Which is the least common multiple, in this instance, of 15 and 6. Remember, multiples are different from factors, right? Multiples are products, whereas factors make products. It's more or less like counting by 6s or counting by 15. So to do a little bit of work here, if you counted by 6s, it would be, know your times tables. All right, 6, 12, 18, 24, 30, and it's a little confusing, right? But this brute force method works. Counting by 15s would be 15, 30, 45, 60. What is the first number that matches? Well, it would be 30, right? That's the LCM, so a 30 would have to go here. And that's the common denominator as well. The lowest common denominator is the least common multiple of the denominators. All right, now, it's all well and good. You could change the appearance of something from 15 to 30 as long as you're consistent. Now you have to ask yourself, what would it take to change a 6 into a 30? In theory, what would you have to multiply by to accomplish that? If you know your multiplication tables, you'll know intuitively, well, it's 5. 6 times 5 makes 30, right? Now again, whatever you do to the top, do to the bottom, and vice versa. Right. So if I'm starting on the bottom here, if I multiply by 5 to accomplish 30, do the same thing to the top. What's 5 times 5? 25. Okay. Now I have an equivalent fraction that is equivalent to 5/6, but it's upgraded so that it has simultaneously lowest common denominator. So there's a lot going on here. All right, now let's do this one. What would it take to get 15 to look like 30? What would you have to multiply by in theory? 2. It's the second multiple, right? So if you did that, if you wanted to change the appearance of 15 to 30, and doing so by multiplying by 2, be consistent. Whatever you do to the bottom, do to the top. All right, what's 13 times 2? 26. Okay, now, once you have matching denominators of 30, and you have consistently altered the appearance of the numerators, what you can do is just write them over their common denominator, which is 30. What would it end up being? It would essentially be 26 minus 25. Right. What's 26 minus 25? 1/30th is the answer. Okay, now I'm going to do the same problem employing the shortcut because it will illustrate the efficiency of it, but the drawback as well. All right. Same problem. You already know what the answer is, 1/30th. All right. If I did 13 over 15 minus 5 over 6, in this case, remember, because you're not multiplying, you can't really simplify diagonally here. You could at best maybe simplify vertically like this, but you're less concerned about that. If we want a common denominator, then we could, as a shortcut, multiply these two things. I know it's a subtraction problem, but this is a shortcut. And so it's kind of bending the rules a bit. Right? 15 times 6 is 90. So that would establish the common denominator as 90. Right? If this is what I'm changing the denominators into, right, just not having to write it twice because I don't have to, then I have to be consistent. So I would have to also multiply vertically this way, diagonally this way. So 15 times 5 would be 75 on this side. All right. So I'm going to park that here. And then multiply diagonally this way, which is 13 times 6. All right. That's 78. All right. 78 would be the figure above the line over here. So what do you end up with? You end up with 78 minus 75 over 90. Right? What is the difference of 78 and 75? Well, it's just 3. And as you can see, the leftover 3 over the leftover 90 would reduce to 30 if you divide each of these by the GCF of 3. Remember, that's the point of GCFs. GCFs are for simplifying. LCMs are for doing the opposite of simplifying. You might say upgrading. Okay? Anyhow, the larger these numbers are, the denominators, the less of a convenience this becomes, because you start reaching outside the realm of familiar numbers. Like, for instance, you may or may not have your multiplication tables memorized up to 12 times 12. And if you do, great, right? That's what you should encourage your students to know, at least. Right? But beyond 12 times 12 is 144, I would argue that the things become less and less familiar. 13 times 13 is 169. I know for a different reason, but I didn't memorize my 13 times tables. I had to figure it out, you know. Right. Anyhow, that's the process. Right. Now, let's say that we had a multi-operational problem, which entails, you know, adding, subtracting, multiplying, or dividing, perhaps all at once. Let's take a look at that. All right. And then I'll stop. This will be the last thing for today. And I didn't do a mixed number problem because you're not going to have it in my lab, but if you did have a mixed number problem for adding or subtracting, make them improper fractions first, then they will conform to the model. Here's 13 over 15 minus 14 over 45 divided by 7 over 9. Now, just remember, the order of operations dictates that we do parentheses first, exponents second, multiplication and division third, and addition and subtraction last. Right? First, second, third, fourth. All right, remember, please, as in parentheses or groups, excuse as in exponents, my dear as in multiplication and division, and addition, Aunt Sally's addition and subtraction. Now remember, multiplication and division are equally important. All right? Addition and subtraction are equally important. They're on the same step. All right? So when you're confronted with a situation, not here, but in other problems of which to do first, it's whichever one is on the very far left. Leftmost. Is what you want to do first. All right, now in this case, you're just confronted with two operations, subtraction and division. Where should your focus shift to immediately? Your focus should be here, right? This is where your eyeball needs to be, right? And since it is a division problem, what we have to do is change this to 14, keep, change, flip. This, keep it as 14 over 45 times 9 over 7. There's still this hanger-on here, and I'm just going to be a good guy and I'm going to leave it there, but you're really just paying attention to what you see encapsulated here. We're going to have to get a new red soon. Okay. So, now, again, you could do it brute force, 14 times 9, figure out whatever that is, and then do 45 times 7, brute force the bottom. But here's a good example of where you would probably want to simplify first just to make it less arduous. So you can simplify either directly above and below the line or diagonally, as long as one thing is above and one thing is below. Don't do simplifying across straight across. All right. There is a relationship between this number 7 and this number 14. So you could simplify before you multiply. 7 and 14 are made of the same factor of 7, that's a GCF. So to simplify is really to divide without thinking. This would reduce to 1, and this would reduce to 2. Right? Same relationship, they're just smaller figures. All right. Now, simultaneously, there's a relationship between 9 and 45 that if you've memorized your multiplication tables, you might identify immediately. As long as one is above the line and one is below the line, you can get away with simplifying before you multiply. 9 divided by 9 is 1, and 45 divided by 9 is 5. Right? Which means, because I'm just running out of space here, what you end up with is really this problem. You end up with the same old 13 over 15 minus the alteration I've made here, which is 2 and 1 and 5 and 1 times that. Now look what this reduced to. 1 over 1, you know, which makes this a 1 that is really superfluous. All right, now do the brute force work. All right, top times top. All right, that's a 2. Bottom times bottom, that's a 5. All right. Again, I'm running out of space, so I'm just going to erase this. Cover up the evidence, right? So, now what do you have? 13 over 15 minus 2 over 5. All right. Now, this is a good candidate for the shortcut, only for the reason that the numbers are relatively small. All right. So, if you want to establish a common denominator, 45 would probably be, I'll do it both ways. You know, 45 is probably the LCD here. I'll do it both ways, just for argument's sake. How do I know? Because if you count by 15s, it would be 15, 30, 45. Right? Or maybe 30, actually. 5, 10, 15. No, it's 15. What am I saying? Stupid. Right? It's 15 itself is the LCM. All right? Which means, in the case of the top figure, you wouldn't really have to do anything. It would just remain 13 over 15. The bottom, at most, you would have to multiply by 3 to upgrade. which would make that 6/15. Okay, and at that point, it's really 13 minus 6 over 15, and that just reduces to 7 over 15. If you employed the shortcut here, you will get something that definitely works, but it will be less, in this case, less convenient. The common denominator would be established by multiplying the denominators, and you would get 75 in that case. Quite a difference, you know, for failing to recognize that 15 and 5 have an LCM of 15. All right. If you multiply it this way diagonally, you will establish 30 on this side of the operator, and 15 times, pardon me, 5 times 13 is 65. Yep. So you'd have 65 minus 30. You can see it's not so convenient in this case. All right, which you only know with enough experience. Even then, you might fudge it like me. All right, so what is the difference of 65 and 30? Just dealing with the tops. 35 over 75. And then you would have to sit here and whittle this down until eventually you get 7 over 15. Let's see. Let's just say you went with divisibility rules, right? Which is that, well, they both ended at 5. So you divide by 5 here. Happens to be the GCF, it looks like. 35 divided by 5 is 7, indeed. And 75 divided by 5 is 15, so very good. Okay. And that is that. Let me just adjust the lights here, turn off the camera, and I'll just remind you what your homework is. Okay. Band-Aid to stop popping off. All right. For homework, I believe that there were 2 parts to 5.3. Do section 5.3, part 1 and 2 in my lab, and that should be it. And remember, they're due by the 27th of October, so you have a while, but don't let it get away from you, you know. It starts to pile up after a while, right? Thank you guys for sticking with me. I will see you again on Thursday. Be careful out there.